Okay. Okay, then we continue on. Okay, we have discussed on the principle of the slope stability analysis. Okay, so now this is extension of the discussion on the slope stability analysis. Okay, so the factor safety is the shear strength at the time of failure, which is we use as a tau F. Okay, compared to the stress acting at the plane, which is the tau M. If the factor safety is equal to 1, okay, so then the slope is in a critical condition. Okay, so this is not good, okay, or wise to design, okay, for the factor safety of the slope is equal to 1. Okay. For example, if any additional load, okay, a sudden additional load, okay, or a loss of strength might be due to the weathering process or due to the what we call as infiltration of water. Okay, so it can sudden increase the driving force. Okay, and definitely it can reduce the factor safety. Okay, so at the time of failure, the shear strength of the soil is fully mobilized along the failure plane. Okay? So the shear strength is represented by the Moore column criteria. Okay, so the shear strength is a part represent the what we call as the resisting force. Okay, so because in this shear strength, okay, either we use the total stress analysis, okay, or the effective stress analysis. Okay. So it may depend, okay, on the type of analysis that we want to carry out. Okay. But definitely, okay, the most comprehensive approach, okay, is the effective stress analysis. Okay. So in relation to the shear strength parameter to be used in the susceptibility analysis, it is important to know the time when the most critical state occur. Okay. So if the most critical condition is predicted at the end of its construction, which is the short terms, then the total stress concept is more appropriate. Okay. So for example, if if you want to investigate, okay, the condition right after the construction's completed, okay, then we may use the short terms analysis. Okay. On the other hand, if the critical condition is predicted in the long term situation, okay, then the effective stress concept is to be applied. Okay. So this is more related, for example, for the construction of earth dam, okay, where there are a pore water pressure, okay, differentiate of pore water pressure, okay, and then we want to look the stability of this type of structure. Okay, so in that case, it's better to use the effective stress analysis. Okay, however, okay, based on my experience, okay, so it is better to carry out for both, okay, the short term and also for the long terms analysis. Okay, because now we have numerical tools or a software, so we may use either the the total stress or the effective stress approach based on the parameter or based on the value that we fill inside the software. Okay, so this depends on the type of the slope equation and on the type of the soil. Okay, for example, the most critical condition for excavated slope is long term, while the most critical conditions for embankment is short terms. Okay, because normally embankment, okay, right after we complete the constructions, okay, the construction will be open to the public, okay, or to the road user. So that is the most critical situation that we need to consider. Okay, while for the excavator, so because the slope will be exposed, okay, to any different weather for a very long period. So that's why we may use the long term approach. But again, okay, it's better for us to consider for short term and also for the long term. And as an engineer, okay, we may use the most conservative value, okay, in our judgment, okay, or justification. Okay.
Doctor,
So
Doctor,
yeah,
one question.
okay.
In your opinion, how long is the duration for short term and also for long term? How do we consider short term? Like how many months?
I guess for the short term, right after complete the constructions. While for the long terms, well, yeah, for the short term, right after we after the complete of the construction, okay. While for the long terms, I'm not pretty sure in times, okay.
So usually we just run both method for any slope analysis, is it?
Yes. Normally we just run both, okay. For example, when I did a consultation work for the road embankment, so I run for both, okay, and then I will use the lowest value, okay. If the factor safety for the lowest value is greater than the factor safety that's been which is 1.5, so it is we consider as a safe. Otherwise, I need to do some adjustment on the slope degree, or make for example any reinforcement or treatment, okay, to increase the factor safety value.
Understand, Doctor.
Okay.
One more question. Sorry. Can you go to previous 2 slides?
Okay.
There's a
Sorry.
T equal to undrained shear strength and then T equal to effective shear strength.
This one.
Yeah. The bottom
Okay.
2 one, I understand the top one, undrained shear strength is for short term. The bottom one is for long term. And then
Yes.
the previous formula we use for the safety factor, the weight cos theta times mu plus C, the previous safety factor. I mean the formula.
Okay.
Yeah. There's a plus C there. So this C is it related to these two undrained shear strength and effective shear strength?
Okay. The previous formula
is a safety factor equal to W cos theta
you can
times
continue
mu
with me,
plus
please.
C. Hello.
Yes. I can hear you.
Okay, the safety factor for the previous few slides is the resistance over driving force, that formula. The W cos theta times mu plus C divided by W sin theta.
This
My
one.
question is, yeah. The C. My question is the C. Is it related to these two C, this undrained shear strength and then the effective shear strength? So if I want to calculate for the long term, the formula I use should be the
Yes. Yes. But this is just some simple explanations, because we may go through later on, okay,
okay.
to derive
Okay.
for the full equation for the factor safety based on the limit equilibrium approach.
Okay. Okay. Thank you.
Okay, sorry about that. Okay. Okay. The previous one is more related to a simple explanation. Okay. Then we may discuss in detail, okay, on how to derive the full factor safety based on the shear strength and also the shear stress. Okay.
Okay, doctor.
So actually the total stress analysis, okay, there are some limitation there, okay, where it could not cater, for example, for a poor water pressure, okay. So that's why most of the cases, okay, um, because it is a short-term analysis, because we assume there are no development of poor water pressure, okay. So that's why for the effective stress analysis, it's more popular to be used because we consider the poor water pressure, okay. Because in here we can include the poor water pressure, okay.
Okay.
Sorry, I guess for the short, for the long term, so it related to the for the how long the structure uh, will be uh, used. Okay, for example, if the road is designed for 50 years, okay, so we just consider it can sustain for 50 years of without any failure. Okay, while for the short terms, right after we complete the construction, so that is the factor safety under the short terms.
Understand, doctor. Thank you.
Okay. Okay. For a slope made of low permeability, such as clay, the ungain assumption may be more appropriate since the dissipation of pore water pressure will take a long time. Okay, for high permeability soils such as sand, where drainage takes place almost immediately, okay, we use the effective stress parameters C and T. Okay. In relation to the type of failure surface, the subsequent parts will deal with slope stability analysis for infinite slope, which is related to the translational type of failure, the analysis of finite slope with planar surface of failure, okay, and circular failure for undrained conditions. Evaluation of stability for a more complex situation should be analyzed using method of slices. Okay, so the first and the second point is more related to the type of the material. Okay, so it depends on the permeability of the material itself. Okay? For example, for clay, okay, so due to the process is the process of the dissipation of pore water pressure will take a long time. Okay? So that's why they use the undrained assumption. While for the high permeable soil such as sand, where drainage take place almost immediately, so they use the effective stress parameter C and T. Okay, but for the clay, if it is a pure clay, so there will be no phi value in that case. Okay, so normally they use the total stress approach. Okay. So in relation to the type of the failure surface, the subsequent will deal with slope stability analysis for infinite slope. Okay, so this is just to explain that we may have a infinite slope analysis, okay, and also on the finite slope analysis, okay, by using this limit equilibrium methods. Okay. So for the infinite slope analysis, okay, normally we use the a linear failure plane approach, okay, where we discuss after we complete this introduction part, okay. And the finite slope, okay, where we discuss tomorrow morning, okay. So they have three type of analysis that we can carry out, okay. For the first one is the planar surface of failure, which is a linear type of analysis. Okay, circular failure for undrained condition. Okay, so this is based on the total stress approach. Okay, evaluation of the stability for more complex situation should be analyzed using the method of slices. Okay, so there will be another approach which is more related to effective stress approach, okay, which is the use of the method of slices. Okay, so this is popular. This is introduced by Bishop. Okay, we have a lot of methods for the method slices, but in our case, we use the Bishop and also the Fillenius. Okay. So causes of slope failure, we have a slope incline. Okay, this is all the causes of slope failure. Okay. So the first is the slope inclination, as I've discussed previously. Okay. So we need to make sure that what we call as the friction angle should greater than the slope degree. Okay. The type of the earth material, so it depends on the material on the soil itself. Okay. So vegetation, okay. Okay, some vegetations, for example, a grass, okay, that can reduce the erosion on the slope surface. Okay. And also there are some plant that can, where the root of the plant can contribute as additional resisting force. However, there are some occasion where this weight of the plant can also contribute for the driving force. Okay. Loss of the shear strength is due to weathering, okay, liquefaction, water infiltration, and seepage. Okay. So we have a weathering where the surface exposed to the what we call as to the hot and dry wet season. Okay. Okay, but this is normally related to the rock structure, rock slope structure. Okay. Then we have liquefactions. So this is more related to what we call as earthquake or seismic situation. Okay. Where due to the vibration, okay, from the epicenter of epicenter from during the earthquake event, okay, so it can change the behavior of the soil, okay, from a very solid particle to a liquid conditions. Okay. So, but it's not happened here in Malaysia. Okay. So normally happen in Indonesia area. Okay. And water. Okay. Due to the infiltration and seepage event. Okay. So this water can contribute, okay, to the slope failure. Okay, because first it can be a part of the driving force, okay? And it also can make the strength of the soil become loose or less. Okay. So for the climate, okay, it depends on the area. Okay. For example, if the area is consists of a very wet or high of rainfall intensity, so it can contribute for the slope to become unstable. Okay. So additional load or field height, okay, for example, when for additional when there are additional load or surcharge on the top of the slope, so it can contribute for the reduction of the factor safety, or the field height, for example, when we construct for the embankment. Okay. It also can contribute to the reduction of the factor safety and also the reduction of the and also the failure of the bearing capacity. Okay. So the last one is the excessive pore water pressure, okay, due to the increment of, for example, of the water level, groundwater level. Okay. Would also contribute for the slope failure. Okay, so the first water is due to the what we call as to the rainfall. Okay, and this is from the groundwater level. But now, due to this slope area is where the location is higher than the groundwater level. Okay, or the slope is not fully saturated. So that's why some of the researcher propose the unsaturated soil mechanics, okay, to cater for this unsaturated area, okay, where the water is far from the slope structure. Okay, so this is related to the this is contribute to the rainfall infiltration. Okay, role of the slope inclination. Shear slope angle is a measure of the steepness of the slope. Okay, slope gradient. Steeper slope increase the driving force. Okay, what we have discussed previously. Steep slope associated with rockfall, sub-arid to arid environment. Okay, so this is related to the area. Okay, if high if the hill hill is too high, so it can reach to within the arid area, arid condition. Okay. Slope of the earth material, slope formed by the weak rock such as shale or have thick soil deposit, typically fail by rotation slide. Okay, so this is that of type of geological formation, lithology. Okay. For example, in Yan area, in Kedah, where they experience the debris flow, so some of the area is covered by shale formation. Okay? So the shale, when it exposed to water, so it become weak. Okay? So that is problem related to shale formation. Okay. So slope formed by hard rock typically fail by translation slide. Okay. Soil slip occur above bedrock and fail by transitional slide. Okay. So this is more related to what we call as a infinite slope failure. Okay. So in subhumid to humid environment, vegetation is thick and abundant. Okay. So so this is more related to area that is very humid, for example, like Malaysia. Okay. So landslide activity include deep complex landslide, earth flow, and soil creeps. Okay. Vegetation influence slope stability by providing a cover that cushions the impact of the rain falling on slope and retards erosion on surface. Okay, so that is the advantage of the vegetation. Okay, vegetation has root system that tends to provide an apparent cohesion which increase resistance to landsliding. Okay. Vegetation adds weight to the slope, increasing the driving surf force. Okay. So the first and second point, okay, so it is more related to an advantage of the vegetation. However, for the third point, it's more related to disadvantage because it can increase the driving force. Okay, so there are a study made in UTM, okay, to identify, okay, what is the advantage of having this kind of a tree, a huge tree, okay, on the slope surface, okay. Either it is proper to have the slope on the toe or surface on the top, okay, because the slope the tree can contribute, okay, the root system can contribute to the to provide a tensile strength, additional tensile strength, okay, where can increase the resistance to sliding. However, the weight of this plant can also contribute to the driving force. Okay. A role of weathering, physical and chemical weathering can weaken slope material, decreasing resisting force. Okay, so this is more related to the rock slope, okay, where they have a grade 1 until grade 6, okay, from fresh rock, slightly weathered rock, moderate rock, okay, up to a residual soil. Okay. So normally for the rock slope, okay, it can be constructed under a 90 degree slope angle. For example, if you heading to the northern part, okay, after the Ipoh. So after the Terowong Menora, okay, so you can find a lot of rock slope. Okay. So actually, I have a project with Plus, okay, to determine the rock structure stability by using qualitative approach, which is RMR and SMR, slope mass rating. Okay. Then we identify that the area majority of the slope are in a good or in a stable conditions. Okay? Although it's been exposed for more than 40 years, almost 40 years or 30 years. Okay? Because most of the rock are considered as a grade 1 and grade 2. Okay? So water can affect slope stability. Okay, shallow soil slip can develop during rainstorm when slope becomes saturated. Okay, slump or transitional slide can develop month of year after slope is saturated. The water can erode the base of the toe of the slope, decreasing slope stability. Okay, so this is the effect of the water. Okay. So for a very short terms, right after the heavy rainstorm, okay, so it can potential to make a shallow failure, okay, on the surface of the slope. Okay, but after for more month or year, okay, after slope is saturated, so it can make uh, 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 what we call as a deep failure, okay, on the slope structure. Okay, so water can erode the base of the toe, okay, especially when it exposed to a river or to the sea side area. Okay, so climate influence the amount and the timing of water in the form of water or snow, okay, and also influence type and amount of vegetation. Okay, so it depends on which area the slope is located. Okay. So for example, for Malaysia, we are more concerned on the rainfall, high rainfall intensity. Okay. Okay, so triggering mechanism, intense rainfall, okay, low or poor water pressure, erosions, removal to support increased slope angle, earthquake loading, the dynamic force, liquefactions, construction activity, okay, if we construct at the toe or the excavation is carried out at the toe, surcharge loading, okay, if additional load is being put on the top of the slope, rapid drawdown, okay, due to the difference, a sudden difference of the water level, especially in the reservoir or on the earth dam structure. Okay. So type of failure, okay, we have 3 type of failure that we discuss in this topic. Okay, so for the first one is the wedge failure. However, it's more related to the rock slope. This type of failure usually occur on a weak plane or weak joint. Okay, so when we hear about joint and plane, or especially joint, okay, so it's more related to rock failure. Circular failure or non-circular failure, okay, this is related to rock to soil slope, okay, where we have homogeneous. If the material is homogeneous, so the failure is potential to have a circular failure. And for non-homogeneous, okay, it can have a non-circular slip failure. Okay, so transitional failure occur when the form of failure is influenced by the presence of weak layer. Okay, so this is more related to infinite slope, okay, where we will have discussed after this. Okay, the failure surface tend to be plain and roughly parallel to the slope surface. So this is the type of the wedge failure. Normally, this is a part of rock structure failure. Okay? Because in rock we have wedge, hopper, okay, slide type of failure. Okay. While this is a circular failure or non-circular failure, it depends on the type of the material. If a single layer, so most probably it can have a circular type of failure. Okay. So, okay, this example is occur in front of the civil engineering faculty in UTM. So we have this kind of failure. Okay, so this is an example for a very good maintenance, because it should cover the blanket should cover for the full of this slope failure. Okay. So it's not a good practice. So UTM has sacrificed this our slope, okay, to show that this is not a proper practice, okay, and it's not a good maintenance way, a good remediation way. Okay, so this is what we call as a method to analyze the circular failure, okay, by using by drawing a circular arch, okay, on the slope structure. Okay. So from there we can calculate for the resisting force and also determine the driving force. Okay, so the W is the weight from the weight of the slope structure. So transitional failure occur when the form of the failure is influenced by the presence of weak failure. Okay. So this is the what we call as a infinite slope. Okay. This is we call as a finite slope because it has a toe, surface, and also top. Okay. While for the infinite slope, okay, we call it infinite because it doesn't the length of the slope is greater than the height of the slope. It doesn't show for any top and toe. Okay. So the way that we analyze is based on the linear type of analysis. Okay. So we just consider for one section where the B, okay. So from this B, we can derive the equation for the factor safety based on the shear stress and also the shear strength. Okay. Okay, due to the length is very what we call as too high or too long. Okay, so it is difficult for us to identify, okay, where is the failure, where is the location of the failure. Okay, but this is a part of the translational failure, okay, on the infinite slope. Okay. So this is another type of failure, okay, where we have a transitional slide, okay, on the weak soil, okay, a rotational slide, okay, and it happened on the base okay, and this one is the rotational slide and happened on the toe, okay, while the D is the failure of which is happened on the slope surface. Okay. So we can see here there are three different type of failure, which is based on base, toe, and slope. Okay. So it is very difficult. Okay, for example, if the slope is not filled, so it's very difficult to us determine where is the potential failure happen at the slope, unless, okay, if we do a lot of analysis. Okay, so from there we can determine where is the most or where is the optimum factor safety value. Okay, so that's why when we read a reference book, okay, so it is suggested for us to use the software rather than we use the manual calculation. Okay, because it's very difficult for us to determine the correct or the optimum location for to determine the factor safety. Okay. So for example, if we are using the slope stability software, so it can run up to 2000 analysis within less than a minute. So from there, it can show where is the potential locations of the slope failure. Okay. So this is a type of a flow, debris flow, and the last one is the block side. Okay, due to the movement of this block, okay, where they have two, we call it as a reservoir, okay, on the left and on the right side. So this is the velocity of the mass movement related to the type of the failure. Okay? So it starts from the lateral spread. Okay? It shows a very slow movement. Okay, rotational slide. So the movement start to increase. Okay, when it comes to debris flow, okay, So it's very huge velocity there. And the last one is the rock fall. Okay. So we can see a lot of this type of failure. Okay. And normally for debris flow, the return, the event normally return for every 100 to 200 years. Okay. So that's why we not hear a lot of debris flow in Malaysia, okay, compared to a normal slide failure. Okay. And the rockfall, okay, I guess in 2004, okay, and there are rockfall in NKVE, okay. Although there are no fatalities, okay, however, the expressway or the highway has been closed for more than a month, okay, and the government need to spend almost 800 million to remove and also to repair the highway and also the slope, okay, to be used by the public. Okay. So this is toppling, okay, and then more related to the rock slope structure. Okay, so this example of the flow failure or debris flow. Okay. So for example, in Yan, okay, there are some area which is covered by the shell formation. Okay. So it exposed to a water, then it become weaker, and then for a last, and suddenly it start to move. Okay. So in that, to prevent for or to minimize this kind of the effect of this event, so the UTM and USM team, okay, has been asked to provide a concept design of a sabo dam. So we the government will reconstruct for a sabo dam, okay, to minimize the effect from this debris flow. Okay. So this is the rotational slide. Okay. Okay. Where we can see here surface of rupture. Okay. So this is the terminology that been used, okay, to explain the rotational slide. Okay. They have a main scarp, okay, which is on the top. Okay. And then it's fall. Okay. This is the main body of the failure. Okay. And then displaced material, okay, up to certain area. Okay, so this is the block slide. Okay, where this block start to move. Okay. Due to the areas being become weaker, okay, because they have a reservoir from the previous what we call previous image. Okay, so important type of mass wasting. Okay, mass wasting is the soil movement. Okay, if you look on the definition, mass wasting, okay, we call as a soil movement. Okay. So this is the type of the soil movement. Slide, the downward movement of coherent block of the earth's material. Sliding along a curved slip plane produce slump block. So this is more related to the rotational movement or the slip circle movement. Okay. Fall, okay. Flow, subsidence, okay, where the sinking of the mass of the earth material below the level of surrounding material. Okay, so this is a slump. okay, or we call as a rotational movement. They have a scarp. Scarp is the top or the toe of the slope. Okay. So humoki is the type of sandstone material. Okay. So we can see the effect of the slam movement or the rotational movement. So this is the area that okay. Okay, so this, the scarp is on the top. Okay. So this is another example. Okay. So we can see that this is the original slope area, okay, while this is the due to the rotational movement or the slump. Okay. So debris flow are the downslope flow of relatively coarse material. Okay, where 50% of particle is debris flow are coarser than sand. Okay. Movement may be very slow or very fast depending on the topography condition. Okay, for example, if on the hilly area, okay, so it's very fast. Okay, so normally it's not only a coarser material, so it also can bring along what we call as a plant, for example, and also the what we call as a boulder. Okay, trunk. They call it a trunk. So mud flow, debris avalanche, and debris flow. Okay. So this is related to a snow avalanche. Then we have a debris flow and mud flow. Okay, small to moderate magnitude event or occasional large magnitude event. Okay, so this example of the debris flow. Okay. I forgot to share the event at Yan Kedah. Okay. I'll update later my slide, okay, to share the event that happened in Kedah under the debris flow. Okay. So this example of the rock slide, rock move because there are nothing hold it back, generally require pre-existing low friction surface. Okay, for example, this is sandstone, so we consider as a rock formation. Okay, so then they have a clay bed. Okay, so this clay bed, if it's exposed to water, so it can make this clay bed become weaker. Okay, and then it can start to move downward, okay, and also bring along the sandstone. Okay. So then, like a clay layer, one is wet, so it can make it become weaker. Okay. Okay, so this example due to the earthquake event. Okay. I guess this image not captured in 1959. Okay. But this is the lake. Okay, where okay, due to the earthquake, so in 1959, okay, so it made this area become a lake. Okay, so 28 deaths in 1959. Okay. Okay, so this is example of a good condition of the slope. Okay, slope in equilibrium with their environment typically exhibit concave. Okay, so this is concave, straight, and convex hill slope profile shown at the left. Okay, slope out of equilibrium typically exhibit anomalous homoky profile shown at the right. Okay? So this is after it's been exposed to a certain period of time. Okay. Okay, stepped topography. Okay. So this is the shale formation. Okay. So we need to make sure we need to have uh, a good need to examine need to provide extra care. Okay, when we have this kind of formation. Okay, stepped topography is not necessarily indicative of slope instability. Can be structurally controlled by underlying stability as shown here. Shale are most often associated with landslide. Okay, so this stepped topography most probably it is safe, okay, because it doesn't consist of shale formation. Okay, but for this kind of formation, it's have shale. Okay, so need to take or put an extra care. Okay, when if we want to do any excavations, okay, on this area or any development on this area. Okay, slope that are experience rampant erosion are typically out of equilibrium and exhibit a truncated concave slope profile shown at left. Okay, so this is example due to the erosion. Okay, where the slope is located near to the sea level. Okay, the slope profile is also influenced by a runoff requirement and the relative position of controlling base level, okay, as cashier. Okay, so this is the due to the runoff, okay, especially on water or river. Okay, no change in the hill profile as channel move away from the ridge line. Okay. Okay. So this is another example to explain on the erosive cycle. Okay. Okay, from it changed from step 1, okay, step 2, step 3, and until to step 5. Okay. So this is another, this is for example, this is the existing slope, then it changed to this kind of new topography. Okay. Okay. So example of homogeneous topography is usually indicative of solidification or active land slippage. Okay. So this example of the area that exposed to landslide. Okay. Okay. So I just share some of failure happen. Okay. The cause of the failure and also the type of the failure. Okay. On this introduction part. Okay. And also discuss on the principle of the slope stability analysis. Okay. So we take a break for 10 minutes and then we will continue for the infinite slope analysis. Okay. Right after we break for 10 minutes. Okay.
Dr. Safwan,
Yes.
yeah, I have a question in the chat. It's
Okay, okay, sorry.
Charles. Yeah.
Yes, because when I go through, for example, to a Hong Kong, for the slope, I'm not sure what yeah, most probably under the Public Works Department of Hong Kong. Okay, so they advise to for any development should located almost twice of the height of the slope from the top. Okay, I guess I will discuss on our next class, not today and tomorrow, on the next class, on some of guideline, okay, for the slope development.
Okay.
Okay, because I have several guideline, especially from the Malaysian authority, okay, where we discuss on the development of the slope area, okay, and also we include any international guideline, especially from the Hong Kong Council of Hong Kong Department of Public Work. Okay.
Okay, noted.
Okay, Z. Okay, thank you. Okay, so we have a break and then we may continue